Sir, so quick question.
Yes.
So, you have tell us about the type series. Say you have a 1 over n plus 1 minus 1 over n plus 3.
Okay.
So, can you rationalize it as there's a difference in like 2, and then say that that's how it plays through the mean before?
Yeah, I think that's a logical conclusion that you could draw.
Okay,
Yeah, that.
I saw. I'm asking because I was watching kind of a video, and it looked like as though this person expanded out several times, maybe like 6, 7, or 8, because it almost looked like you needed to go a little further out somewhere to see something. Or to see
Yeah.
the picture.
It depends on the number of terms you go out to see the cancellation. Kind of depends on you. Like, you might not see it right away. Some of them you can't see until you go out a certain number of terms. So like the 1 over n plus 1 minus 1 over n plus 3, you would have to go out at least 2 terms to see a single cancellation.
Okay, see, that made sense.
Yeah.
I was like, but it looked as though to see the whole pattern, you had to go out.
Yeah.
It's kind of weird.
How are we doing here?
You know, we're pushing you.
I got your text. I've been busy. Yeah.
So if I have, let's just say something real basic, like 6n, and I want to make a sequence that does each index position twice. So in other words, give me 6 times 1, and give me 6 times negative 1, then give me 6 times 2, and then give me 6 times negative 2. Like, how would I write that mathematically?
So you want like 6, negative 6, and then you want
So
12,
basically,
negative
each index
12.
you counted twice, give me a positive version and a negative version of each index. And then
Gotcha.
you
Mm-hmm.
Okay, that's not too bad.
And if it were a function, it could be a parabola.
So another way you could do it is say, I want 6 when it's odd.
Okay, so there was only like 1.
Or sorry, 6. You want like 6, 12, 18, right, when you're odd. And when you're even, you want negative 6, negative 12. So what you can do is, every time you can have two terms. Every time you have an odd, you make one of the terms vanish, and you make the other one appear.
Skipping it because you would never get.
Well, it depends on how you write it. You could have it do one thing when it's odd and one thing when it's even.
So like for instance, let's say you were at index 1. One side, because that's odd, would then give you the result of, but you'd never be able to go back and capture the negative one. So
I think you could. You have time after class? Okay, we could probably figure it out pretty easy. Okay, let's get started. I'm already recording. So I looked at our schedule, right, where we are in the class. We are behind. Okay, I've never not finished chapter 8 in the Cal 2 class, but we are at risk of not finishing chapter 8, which I think is not good. So what I'm going to ask today is that I've always loved to entertain all your questions. You always come with good questions, but we need to move, all right? So if you have questions, jot them down, and let's proceed through the material, all right? And then after class, we can talk in more depth about anything else you might have, all right? And then to top it all off, I'm required to give you this survey. Our class got selected for a survey. So what I'm going to do for this is I'm going to administer this. I'm going to give you an extra credit for this. It's going to replace your lowest quiz grade, all right? I don't know, how many quizzes do we have? We only have a few, right? 4? So yeah, I'll replace your lowest quiz. How about that? If you do the survey, but there's a catch. You have to do it after class, and it just needs to be turned in to me today by 3 o'clock. So you can take it with you, go finish it, bring it to me later, all right? It's optional, but not really if you want your lowest quiz grade replaced, all right? That fair to you? Fair? Madison, yes? Everyone? Anyone object? No objections? Sure? Okay, all right. Let's get down to business. So we were talking about the comparison test last time. I'm putting it off camera because you have it in your notes. Comparison test said if we're ever dealing with a series that has positive terms only, right, then what we do is we find another series that has positive terms as well, and we compare the two. And if the one that we are comparing it to converges, then we have to show that the sequence on the original series is smaller than the sequence on the one we're comparing it to. If we can do that, then the original series will converge. And then the reverse of that is if the one we're comparing it to diverges, then we have to show that inequality the other way around. And if we can show that inequality the other way around, then the original series diverges. So here's an example. We're going to go through these 3 examples, and then we'll hold off on this one, and then I'm going to show you a new test. We're going to go through these 3 examples again using the new test, and then we'll go after that one. All right, so when we look at this here, let's just run through things. Nth term test. Let's let n go to infinity, you get 0. That tells us nothing. It's not geometric, it's almost geometric because we have 3 to the n. But the plus n makes it not geometric anymore. So it's not geometric, it's not harmonic, not constant over linear. It's not telescopic because I can't split it up and start getting things to cancel. What else do we have? Integral test, do I feel like integrating that? I don't feel like integrating that. So we have comparison test. So I look at that and I say, hey, it was almost geometric. Like if that n wasn't there, it's almost geometric. So that's a good place to start. So I'm going to compare this to sum n equals 1 to infinity of 1 over 3 to the n, which is really sum n equals 1 to infinity of 1/3 to the n. That's just me realizing you could rewrite this as this. And that's geometric with r being 1/3. And of course, that's less than 1, so this converges. So we have I'm comparing it to a convergent geometric series. And because this is convergent, what I need to show is that all of these guys right here stay smaller than all of these guys, right? So I want to show, WTS, I want to show that the 1 over 3 to the n plus n, that's the sequence here, these guys are always smaller than those, or equal. If I can show that that's true, then I'm done. Then whatever this one does, that one does. Again, the whole idea is that if these add up to be a number, it converges. If this adds up to be a number, and these are smaller than those, then those should add up to be a number as well. Even though it doesn't have to be the same number, it's some number. All right, and then here I can just like cross multiply, right? I can just get rid of this, put it over there. I do not have to worry about flipping the inequality because I know 3 to the n is a positive number. I also know that 3 to the n plus n is positive because, again, n is natural numbers, so we don't have any negatives to deal with. And then I can subtract 3 to the n on both sides, and I get n must be greater than or equal to 0. And that's always true, at least for our series, right? It's true. And so this is, we're done. Basically, we can say, therefore, 3 dots means therefore, the original series, what? Converges. Done. Okay. First one's done. Next one. N cubed over n to the 4th. This is very similar to a problem we did last class. Converge or diverge. So I look at that and I'm like, okay, I run through all the different things and I say, okay, finally I get to where I'm like comparison test. All right, let me try to compare it. And the way that I think about this is when n is really, really big, right? When n is a huge number, this minus 1 really doesn't make much of a difference, does it? Like a minus 1 here really doesn't do much to an n to the 4th power when n is real large. So I'm kind of looking at this like it's almost like n cubed over n to the 4th, which would be 1 over n, wouldn't it? 1 over n. So that's kind of, I have to come up with something to compare it to. That has to come out of my brain. And so I think I'm going to try 1 over n, and I don't know, it may or may not work, all right? But I'm going to try it. So I'm going to compare this to 1 over n. 1 over n is harmonic, and that harmonic series diverges, all right? If you're coming in a little late, I made an announcement at the beginning of class that we are behind this class. I'm moving, the train is moving down the station, or out of the station, and so I'm not going to be entertaining as many questions, so if you have questions, please jot them down. I'm not saying don't ask me anything, but if it's something more abstract, we're not going there, all right? All right, good? Divergent. So if it's divergent that I'm comparing it to, then I know that these add up to be some infinite number, right? It becomes infinite. And so if I can show that these are bigger than those, then this should also be infinite as well. So I want to show that n cubed over n to the fourth minus 1 is bigger than or equal to 1 over n. And then I can do that same cross multiply thing. Go ahead. That's what you have to understand here. You have to understand, if this diverges, then this adds up to be infinity, right? We need then that this is bigger than that, right? Think about it. If these are bigger than those, shouldn't this add up to be something infinite? Now, if this converged, that means these add up to be a number. So I want to make sure that these are smaller than those, because these would add up to be something smaller than that number, which means this would add up to be a number, which means it converges as well.
So the second one dictates basically what you want out of the first.
This one dictates what inequality you have to show. And it's on the page as well, like it's on your cheat sheet. It shows it. All right, so I'm multiplying here and here. Subtract n to the fourth on both sides. Subtract, you get 0 is greater than -1, that's true. Right, that's always true. So, yes?
Is it a problem that our original series is undefined?
Oh, I put 2, sorry, I put 2 here. I put 2 here, I forgot to put 2 here. Yeah, thank you. I forgot to put 2 there. Yeah, because if you try and plug in 1, you get division by 0. My apology. Good catch. All right, so therefore, whatever this series does, that series does. The original series, notice I'm writing my conclusion, right? I'm writing my conclusion. You need to do that as well. Converges. All right, 2 down. Let's do another one. Diverges. Diverges. I'm having a week. This week has been something else. Have I told you about the math purgatory? Right.
Yeah, I think
I'm going to be in, like, I believe at some point I'm going to be in math purgatory, and they're going to bring up all the mistakes I made in class. All right, next one. This one right here. Look, there's not much difference between these two, is there? Okay, just a plus right here. And actually here I can have a 1 because I don't have division by 0 anymore. All right, so let's see.
that was supposed to be n equals 1 as well.
This one is n equals 2 because you can't plug 1 into this.
Oh, okay.
This one started at 1. There's no problems there. Okay, so when I do that, it's the same argument, right? That 1 is really insignificant, so I would like to compare it to that again. Right? I mean, it looks like this. So what do I want to show? Well, this one diverges, right? And so I know that this adds up to be an infinite amount, so I want to show that those are bigger.
Yeah.
And this time, when you do your cross multiply here, you get n to the fourth is bigger than or equal to n to the fourth plus 1. And when you subtract on both sides, you get 0 is bigger than or equal to 1, and that's not true.
Which means it's not divergent, therefore it's...
No, this means that the test fails.
Yeah.
All this means is that this test doesn't work. We cannot draw the opposite conclusion from this. So this, therefore, test failed. And that's it. We have to move on to another test. All right? Okay, that's it. We're going to save this one. We're going to come back to it later. All right? That's the comparison test. The idea is that you're finding something to compare it to, figure out if it converges, diverges, do the inequality, and hope that you can draw a conclusion. Yes?
If you fail the test, does it mean that you have to, that it's possible that you chose like a bad
It's possible that this was chosen wrong. You could try something else. We could try a different one. We could try something else to compare it to. And then it might work. But as of right now, that comparison told me nothing. All right, now we have within this idea of the comparison test, we have an additional test, which is like almost like another version of this test. It's called the limit comparison test. And here's the difference between them. You're going to love this test, all right? I don't know about love, but you're going to like it. So basically, it's all in the notes here, but basically what this test says is this. The limit comparison so this is the comparison test. This is the limit comparison test. Different wording there, right? What it says everything it says here, okay? So it says if you're given some series with positive terms, you compare it to something you come up with, right? As long as it has positive terms or non-negative terms, you compare it to something, and then this is where we did the inequality, right? With the limit comparison, you don't do the inequality. Here's what you do instead. You take the limit as n goes to infinity of the a sub n, which is that sequence, divided by this sequence, b sub n, and you see if you can get an answer from this. And what you're hoping for is that you get a constant. Okay? You need this to be a constant. Hold on. So c is a constant. Not 0, okay? Sorry, it should be positive constant. C is a positive constant, which it should be anyway because these are both positive terms, but it's a positive constant, not 0, not infinity. All right, so what happens if you do this, you have your original series, you compare it to something, and if you get a positive constant, if you get that, a positive constant, then whatever this does, that does. So if this diverged, that diverged. If this converged, that converged. So if this, I should have put if in front of this, if this is true, then they do the same thing. This is all in your sheet, right? Your cheat sheet. They do the same. They do the same exact thing. Let's do the same 3 problems we just did. The same 3 problems using that version of the limit comparison instead of the original comparison. So let me do the first one. 1 over 3 to the n plus n. What did we compare that to? We did 1 over 3 to the n, didn't we? And what does this series do? It converged, right? This was a convergent series. So we had the original series. We want to know what this does. I compare it to that. But now I don't do inequalities. What I do is I take the limit as n goes to infinity of 1 over 3 to the n plus n over that sequence, 1 over 3 to the n. And before I do any sort of work here, let me just flip it because a fraction over a fraction is the same as multiplication of the reciprocal. So this is limit n goes to infinity. I'm just going to flip that one up so it becomes 3 to the n over 3 to the n plus n. And I cannot cancel these, right? Because I have 2 terms in the bottom, 1 in the top, so I can't do that. Let's take a limit. N goes to infinity. That goes to infinity, right? 3 to the infinity goes to infinity. 3 to the infinity goes to infinity, plus infinity. So infinity over infinity. L'Hopital. L'Hopital. All right, now you have to go back to Cal 1. The derivative of 3 to the n is 3 to the n times natural log of 3. So this is back in Cal 1. We had the derivative of a to the x is itself times natural log of a. I'm using that property from Cal 1, taking derivative of that, becoming this, over. Derivative of it, that again is 3 to the n times natural log 3 plus derivative of n is 1. Now, do it again. Let n go to infinity. N goes to infinity. This is infinite, isn't it? Yeah. Infinite over infinity plus 1, still infinity. So I'm going to do L'Hopital again. On this step, things are going to get nice. Remember, natural log of 3 is just a number, so I'm going to ignore it. So I take derivative of 3 to the n again, and I get 3 to the n natural log 3. That's derivative of this. But then I still had a natural log 3 there, so I have 2 of them. Over the bottom is the exact same thing, isn't it? Yeah. Because this derivative is the same as that derivative, but now the derivative of plus 1, that goes to 0. Let's get the exact same thing on the bottom. Right? And that's just 1, right? Because they just reduce out, and you just get 1. And 1 is a positive constant, isn't it? 1 is a positive constant. So that tells me that whatever the one I compared it to did, that one must do the same thing. So I'm done. So this is a positive constant. Therefore, the original series converges. That's it.
So can you
Yep.
always do that rather?
Hold on. Yep.
I mean, there's a quick question on the previous step. Couldn't you just been able to cancel the 3n already?
There was a plus 1 down here.
But it's like multiplying. The 3n.
3.
Oh.
Yeah, the 3 to the n.
These?
Yeah.
No, because of the plus 1. That would be like me doing this. 4 over 4 plus 1. You can't cancel the 4s.
Oh, yeah,
Right?
I see what you mean now. Yeah.
Now, on the next step, I could. See, here I could because I no longer had addition on the bottom. I just had multiplication all the way, so everything goes. And I just get a 1.
Can you explain just that last step?
What, this?
That one. How do we get there?
The derivative, so this is a constant, I ignored it. The derivative of 3 to the n is this,
Okay.
and then there's the constant I ignored.
Oh, so you just did the same thing on the bottom.
And on the bottom, I did derivative of that, which is identical to the top, right? And then plus derivative of 1, which is 0. And then everything just reduces. Yes?
Sorry, it's a quick question. So can you always do the limit comparison test instead?
Yes.
Okay.
You can always do this test. Yep, this is, sometimes it's better than the other way, sometimes the other way is better in this way. You won't know until you do it. You're going to just have to do the test and see what happens. Let's do this one. All right, I'm going to work right here. So when we did this one, right, a second ago, we said, hey, that looks a lot like 1 over n. So I'm going to compare it to 1 over n. And that's divergent because it's harmonic. Or you could say it's a p-series p1. Either way. All right, so now I'm going to take a limit. I'm going to take the limit as n goes to infinity. I'm going to take that sequence, n cubed over n to the 4th minus 1 over 1 over n equals limit n goes to infinity. Okay, flip it. When I flip this up like this, 1 over n, it'll become n over 1 right here like that, and then that n jumps up there, becomes n to the 4th over n to the 4th minus 1. Let n go to infinity, you get infinity over infinity, L'Hopital. 4n cubed over 4n cubed again. And hey, that's going to just reduce out and become a 1 again. It's a positive constant. Whatever that one did, that one does as well. Okay? You like it? Love it? Like it? Love it. Okay, therefore, the original series converges. This was a 2 again. Sorry, I put a 1 there again. This one diverges. Yeah, that was divergent. This one's divergent as well. Okay? Let's do the third one that we actually got stuck on, didn't we? We got stuck on this one. Can I do it really fast? Look, what changes? What's the only thing that changes? This is a plus 1. Okay, I'm going to do the same thing over here. Compare it. This is a plus 1. This is a plus 1. And does that change the derivative? No. So you get the same thing, don't you? Positive constant. Which means that whatever that does, that does. We actually have an answer this time, right? We actually got to the result. So this one, with a plus 1 down here, diverges as well. So that shows you where one test didn't work, but another version of the same test did work. All right, let's do the one that we have conveniently avoided. I feel today like a professor I had back in my days sitting there as a student. Have I told y'all about that professor I had that didn't talk to us? Yeah, that's how I feel today. Although he literally did not talk to us. I mean, he did not talk to us. I told you what it felt like, right? I showed you what it felt like? Yeah? Like, I mean, this is exactly what it felt like. That's what his notes were like. It's like, try and keep up. All right, here we go. So look at this one right here. Let's try and compare this to something. Natural log n over n squared. So something subtle. When n is 1, natural log of 1 is 0, right? Okay, but after I get past 1, this natural log is positive. So in the very beginning, I get a 0, but then after that, I have positive terms, right? So I can do comparison because it's going to be positive and it's going to like stay positive. It never goes negative, right? So I'm sitting here, I'm like, okay, what do I compare this to? What do I compare this to? I don't know. 1 over n squared? Let's go for that. I mean, that's kind of like ignoring the natural log and saying, hey, maybe this is kind of like 1 over n squared. Now, that's a guess, right? I'm hoping this is what it is. Now, I need to know what this does. This is a p series, right? P is greater than 1. And that means it converges, right? You have to know that. Don't compare it to something you don't know what it does, right? I mean, because then you say, oh, okay, yeah, that one does what that does, but I don't know what that does, right? You have to compare it to something you know. And so I now have a choice. If this is convergent, I have to show that this is smaller than that, or I do the limit comparison test. What would y'all like? Limit comparison. All right, so I'm going to use this test here. Take the limit, let n go to infinity, natural log n over n squared over 1 over n squared. So it's that sequence over that sequence. Now I'm going to flip. When I flip, what happens? N squareds cancel, and all I'm left with is natural log n, right? And when you let n go to infinity there, you get infinity. And what does this say? You have to have a positive constant. Can't be 0, can't be infinity. So it fails. The test fails. This does not tell you that it does the opposite of that. Okay? It just tells you that the test failed. So limit comparison didn't work. So maybe we picked the wrong thing to compare it to. Or maybe we should use that instead. Let's do that instead on the same series. So this failed, right? Fails. So now let me try that comparison over there. So for that comparison, what I want to show, like I said, because this one converges, I want to show natural log of n over n squared is less than or equal to 1 over n squared, right? Because this one converges, I've got to show that this stays bigger than that. Multiply both sides by n squared, and what do you get? And they'll cancel, right? Won't they? I mean, you can just basically get rid of them. So this is this. Multiply both sides by n squared. Is that true?
Not at all.
No, right? Like natural log of 1 is 0, right? Natural log of 2 might be less than 1, but the natural log function does this. And it starts to grow without bound, right? So this is not going to hold true all the time, right? Especially when n starts to get big. And we need this to be true, right? And it's not always true. So this fails. So that would make me think maybe what I picked to compare it to wasn't a good choice. Good job. I'm kidding. So this is part of the kind of struggle, right? Is figuring out what to compare it to. So you want to try something else?
Yeah. N over n squared?
N over n squared. Well, that would be the same. That would be the same as this. N over n squared would give you the exact same. Oh, you said n over n. I'm sorry. So that'd be 1 over n.
Yeah.
Okay. So instead of doing natural log of n and saying, hey, let's just say that that's like a 1, let's do an n up there. N over n squared. We can try it. I like it. N over n squared is like 1 over n. Right? That's really what we're doing here. This is a, you could do p series, couldn't you? You say it's p or harmonic. But what does it do? It diverges. So now I'm comparing it to a divergent series. So let me try the limit comparison first. Let me try that. If I'm moving too fast, I'm sorry. It's on camera. It's on camera. I'm sorry. I don't know what else to tell you. Okay, so I'm going to take the limit of that sequence over that. And then when I do my thing and flip it, I get natural log n over n, right? Because one of the n's cancels. That limit gives me infinity over infinity. So I do L'Hopital now. Derivative of the top. Derivative bottom. 1. What does that go to? 0. And what does that tell you? Nothing. Fails. Man, this one's pesky, isn't it? This is real pesky. It's just nothing is working, right? Let's try the inequality. Let's try the inequality, all right? So for the inequality, it fails, right? Fails, all right. So for the inequality, I want to show, because this one is divergent, I want to show that these are bigger than these. Multiply both sides by n squared. Over here, you'll get natural log n. Greater than, over here, when you multiply both sides by n squared, you get n. Is natural log bigger than n? Go back to the graph. This is like me saying, is natural log of x bigger than or equal to x? So isn't this what the function f of x equals x looks like? And natural log, doesn't it look like this? Right? Now, they may hit each other at some point, but I'm just saying, like, it stays below. What's wrong? Yeah. So, yeah, they don't hit each other, do they? They don't. So, yes?
So when you're asking if something's bigger or larger, are you saying, like, when it goes towards infinity,
To-
or it always has to be below or above?
It says, as we go to infinity, we need this inequality. In order for this to be true, for us to conclude this, right? To be able to conclude that this diverges, we need this to be true as n gets bigger and bigger and bigger. So in the beginning, if there's a few places where it's not okay, that's all right. Just as it goes to infinity, we need it to hold. Okay? So this doesn't hold, not as we get further down. So this fails again. So guess what we're going to use? Nothing. We're going to quit. We're going to quit. Oh, integral test, right? Is that what I heard?
I said a new test.
Oh, a new test. Integral test might work for this, actually. The integral test might work, but we're going to need a new test. So the point of this problem was to show that, look, as good as comparison test is, and as good as the limit comparison test is, there's not one test that solves all of our problems, all right? If there was, then we wouldn't go through all these tests, right? I would just give you, hey, everyone, here's in Cal 2, here's the one test. But we have to have several to be able to handle different scenarios. All right, so let's talk about some other tests. This is an open question. The one in the box is an open question. We have not answered that, right? Okay.